A mystery interstellar object just had its deepest secrets decoded by the most powerful telescope humanity has ever built. And what came back is nothing like what scientists expected. Not because the object is dangerous, not because it is behaving impossibly, but because the chemistry locked inside it points to a place and a time in the history of the galaxy that nobody had considered seriously as a birthplace for anything that could reach us. Something that formed 10 to 12 billion years ago, in conditions so cold and so remote that the ice inside it has never been fully reprocessed, has just passed through our solar system. And we caught it. Just barely. And what Webb found when it looked at that ice changes what we thought we understood about where comets can come from. This is the full story of what James Webb Space Telescope found when it turned its instruments on 3I Atlas, and why the researchers who ran the analysis used a single word to describe what the data showed them. Surprised, 3I JWST Atlas was discovered on July 1st, 2025, by the Atlas Survey Telescope Network in Chile. Within hours of the discovery announcement, orbital calculations confirmed what the numbers were showing. This object was not from here. Its trajectory was hyperbolic with an eccentricity of 6.14. An object on a gravitationally bound orbit around the Sun has an eccentricity below 1. And eccentricity of 6.14 means the object arrived from interstellar space, traveling at a speed so far beyond solar escape velocity that nothing our solar system could have produced sent it here. The comet was moving at speeds in excess of 130,000 miles per hour in an unusually flat trajectory, inclined only 4.89 degrees from the ecliptic plane. It made its closest approach to the Sun on October 29, 2025, at a distance of about 1.35 astronomical units, roughly the distance of Mars, and it has been heading back out of the solar system ever since. It is the third confirmed interstellar object ever detected. The first was 1I Oumuamua in 2017, which showed no gas emission, no coma, and acceleration that defied simple explanations. The second was 2I Borisov in 2019, which behaved like a perfectly normal comet in almost every measurable respect. 3I Atlas is different from both. Its chemistry is unlike anything observed in solar system comets, and researchers estimate it may have formed 10 to 12 billion years ago. 10 to 12 billion years. The universe itself is only 13.8 billion years old. Whatever built 3I Atlas did so when the Milky Way was young and the stars forming inside it were nothing like the stars forming today. James Webb observed 3I Atlas on August 6, 2025, before perihelion, using its near-infrared spectrograph instrument. The science team received approval to interrupt Webb's planned observation schedule to point at the comet while it was still inbound and active. The results confirmed what earlier Sphere-X observations had detected. 3I Atlas was producing a carbon dioxide-rich cloud of material in quantities that made it the highest carbon dioxide to water ratio ever measured in any comet. Not the highest among interstellar comets, the highest ever. The CO2 dominated the outgassing at 87% of the total gas mass being released, with water contributing only 4% and carbon monoxide the remaining 9%. Most solar system comets show less than 1 part CO2 for every part of water. Some show far less. 3I JWST Atlas was doing something categorically different. Then Webb came back in December 2025 after perihelion. The comet had passed closest to the Sun, been warmed through its inner passage, and was now heading back out. Its ancient ice, frozen for potentially 10 billion years, had been heated for the first time. The chemical inventory inside it was being exhaled into space, and Webb's MIRI instrument, the mid-infrared instrument, collected the first mid-infrared chemical fingerprint ever taken of an interstellar object. The observations were taken on 2 separate dates as 3I Atlas traveled back out of our solar system after its closest approach to the Sun. What MIRI found was methane. Webb sniffed methane from the interstellar comet in mid and late December, roughly 2 months after perihelion. The amount of methane relative to water was surprisingly high compared to other solar system comets. The methane production rates in the 2 observing sessions were 13.7% and 27% of the water production rate, respectively. In solar system comets, methane is typically detected in only trace amounts. In 3I Atlas, it was a major component of the chemistry pouring off the surface. Both the methane detection and the confirmed carbon dioxide abundance point to a very different formation, environment and chemistry, than the vast majority of comets that formed within our solar system. But the methane finding, striking as it is, was not what surprised researchers most. The paper that stopped the scientific community in its tracks was published on June 22, 2026, in the journal Nature, by a team led by Martin Cordner, astrochemist at NASA's Goddard Space Flight Center. It used the NIR-SPEC instrument, the near-infrared spectrograph on Webb, to map specific chemical contents of 3I Atlas as the comet moved away from the Sun in December 2025. And the number that came back from that analysis is the one worth sitting with. An IR spec revealed exceptionally high levels of deuterium, about 30 times more than seen in solar system comets. Deuterium is heavy hydrogen. An atom of hydrogen normally has one proton and no neutrons in its nucleus. Deuterium has one proton and one neutron. It is heavier. It is produced in the first few minutes after the Big Bang, distributed through the universe, and incorporated into molecules in specific ratios, depending on the temperature conditions during formation. Cold environments favor higher deuterium to hydrogen ratios. Warm environments, over time, break down deuterium enrichment. The sun's own heat has been slowly processing the icy material in our solar system for 4.6 billion years, redistributing deuterium and bringing its ratios in solar system comets down toward values that reflect that long, warm processing. Webb captured chemical ratios of carbon and deuterium that are not found in solar system comets. Working. Backward, astronomers use the components that make up 3I Atlas to understand the environment in which it formed. What the ratio pointed to was a formation environment so cold, so far from any star, and so early in the galaxy's history that the deuterium in 3I Atlas had never been significantly reprocessed. The ice inside this object has been sitting at temperatures close to absolute zero for most of the time the universe has existed. It formed before our sun existed, before the Earth existed, possibly before the Milky Way had settled into its current structure. The material that built 3I Atlas was assembled when the galaxy was in its first few billion years of existence and has been essentially frozen in place since. During its formation, the material that became incorporated into 3I Atlas was likely exposed to plenty of radiation, but not any long-term warmth that would have reprocessed its heavy water ice with deuterium into the type of water ice we find in our own solar system. The implication is direct. This object is not just a comet from another star system, it is a comet from another era of galactic history. The star or stars it formed around are almost certainly long dead. The planetary system it originated in, if there was one, has had billions of years to evolve, change, or disappear entirely since 3I Atlas was ejected into interstellar space. And the chemical conditions that produced it, the cold, radiation-rich, deuterium-rich environment it formed in, represent a class of planetary formation chemistry that our solar system never went through. A separate complementary study used the European Southern Observatory's Very Large Telescope to analyze carbon and nitrogen, isotopes in 3I Atlas through its cyanide emission. Stephanie Milam of NASA Goddard, co-author of the Webb study with Cordner, said, "For us as scientists, finding these rare isotopes is fascinating, but the bigger picture here is looking at the possibilities of prebiotic chemistry elsewhere in the galaxy. So far, we know of only one place in the vast cosmos where chemical ingredients led to life, our solar system, our Earth. Analysis of these interstellar objects is a major step towards learning how common, or uncommon, the conditions for the evolution of life are in the universe. That framing is worth unpacking. 3I Atlas did not arrive carrying life. It did not arrive carrying signals. It arrived carrying chemistry, ancient chemistry from a cold, distant corner. Of the early Milky Way, chemistry that formed under conditions we have never directly sampled before. The carbon ratios, the deuterium levels, the methane and carbon dioxide proportions, all of them together constitute a chemical fingerprint of a planetary formation environment that existed before our sun was born and that no instrument had ever measured directly until Webb pointed at this object and collected its spectrum as it left. That is what is remarkable about the June 2026 Nature paper. Not that 3I Atlas behaved unusually, not that it moved in unexpected ways, but that its chemistry is a direct sample of a chemical environment we could not have accessed any other way. Interstellar objects are the only directly observable samples of icy material formed around other stars. Everything else we know about the chemistry of distant star-forming environments is inferred from telescope observations of those environments from a distance. 3I Atlas is not observed from a distance. It is here. It passed through our solar system. Its molecules were collected directly by instruments orbiting the same star it was passing. Those molecules were 10 to 12 billion years old. There is one more piece of the picture that arrived with the post-perihelion data. Webb observed a sharp decline in gas production as 3I Atlas moved farther from the sun, with water showing the most pronounced drop. Water, which is less volatile than methane or carbon dioxide, is quicker to shut off its gas production as the comet gets less heat from the sun. The pattern of shutdown tells scientists something about the layering of ice inside the nucleus. Highly volatile species like methane and carbon dioxide continue producing gas at distances where water has already shut off. The sequence in which different molecules stop venting as the comet cools is a direct readout of which ices are closest to the surface and which are buried deeper, carrying information about how the nucleus was assembled layer by layer over billions of years. Researchers estimate that 3-Ag Atlas may have formed 10 to 12 billion years ago. At the upper end of that range, the object is only about 1.8 billion years younger than the universe itself. It has been traveling through interstellar space, possibly for most of that time. Billions of years of exposure to cosmic rays have altered the chemistry of its outer layers in ways that complicate reading the original material. And yet the deuterium signal, buried deep enough to have survived the radiation processing, still carries the original fingerprint of the cold, ancient environment in which it formed. The outer layers have been changed by the journey. The inner ice preserves the origin. Alice Fisher, speaking from NASA headquarters, noted that although 3K Atlas is not believed to pose any threat to Earth, NASA's space telescopes help support the agency's ongoing mission to find, track, and better understand solar system objects. The comet has no threat. It is already leaving. Its closest approach to Earth was 1.8 astronomical units, well outside any dangerous range, and it is now heading back into the interstellar dark that produced it. It will not return. There is no second pass. The December 2025 Webb observations caught it during the last practical window when enough heat-driven outgassing was still occurring to produce a readable chemical spectrum. A few weeks later, the gases were shutting down. A few months later, the object had faded beyond what most instruments could track usefully. The window was always going to close. What matters is that Webb was pointing at it when it was still open, and the data that came back from those weeks of observation produced a paper in Nature, a detection of the highest deuterium enrichment ever seen in a comet, the first mid-infrared fingerprint of an interstellar object, and an age estimate that places the formation of 3I Atlas in the first 2 billion years of the galaxy's existence. The truth about 3I Atlas is not dramatic in the science fiction sense. It is dramatic in the real sense. Something older than our sun, carrying chemistry from a cold, early corner of the Milky Way, passed through our solar system in 2025 and 2026. James Webb had time to smell its breath before it left. And what it smelled surprised the researchers who built the instrument and designed the observation and spent months analyzing what came back. We have sampled the chemistry of the ancient galaxy. It was frozen inside a comet, and it just passed through.